So today what I'm going to do is to give you the detailed proof of our Galois theory. So let us state the theorem one more time. Theorem, let K be a finite normal extension of F and E be an extension of F such that F is a subfield of E, which is a subfield of K. Then let G of K over F be the Galois group of all automorphisms on K leaving F fixed. Then there exists a map lambda from the collection of all extensions of F to the collection of all subgroups of G of K over F. So then this map has the following properties. So the first property is the definition. Lambda of E is equal to G of K over E. Lambda is a map from collection of all extensions to the collection of all subgroups. E is an extension. You are picking an extension E of F. So you are mapping F E to the Galois group of K over E. So there is nothing to prove here because this is the definition. All we need to do is a valid definition. It is clearly a valid definition because you are mapping an extension to a unique subgroup of the Galois group. So our proof starts with the second property. And the second property is E is equal to K, the fixed field of K over the Galois group of K over F. Or this is equal to K of lambda of E. The second property states really, so we are going to start the proof from here. So second property states that every extension is a fixed field. And we are going to make use of this result to show that this map is 1, 1. So to prove this, we are going to make use of one result which we established earlier, and that is if E is a finite extension of F, then F is a subfield of the fixed field of G of E over F. Sorry, this is actually going to be E. So we are going to use this straight away here. So clearly E is a subfield of K of G over K over E. We are replacing E with K and F with E. So one part is done. This is a subfield of this. Now we need to show that the fixed field is a subfield of the extension. The way we are going to prove that is, we are going to prove that there is no element in the fixed field that are not here. Here you are saying, this says that every element of E is in the fixed field. Now we are going to show that there is no element in here in the fixed field that is not here, which means that this is a subgroup of this. So for that, what we are going to do is, so it is the picture is like this. This is K, this is E, and this is F. So we are going to pick an element outside E, so that we'll say that alpha does not belong to E. If alpha does not belong to E, then we are going to prove that alpha is also not in here. That is a plan. So we'll say let alpha belongs to K minus E. It has to be in K, otherwise it doesn't make any sense. So we are going to use this. Now, so this implies alpha is algebraic over E, because E is a finite extension of E. K is a finite extension of E. So this means that there exists a P of X, and that is the irreducible polynomial of alpha over E. And beta different from alpha be a conjugate of alpha. Then there exists a conjugate isomorphism alpha comma beta from f of alpha to f of beta, such that alpha of psi of alpha beta of alpha is equal to beta. Because K is a finite extension, this can be extended to an automorphism on K. So psi of alpha comma beta can be extended to an automorphism tau from K to K, and that implies tau of alpha is equal to beta. So tau actually belongs to G of K over E. Okay. Now, what is a fixed field of, what is the definition of fixed field? K of G of K over E. This tau belongs to the Galois group of K over E. And what is the fixed field over this Galois group? Those elements from K that are fixed by every automorphism in here. But we found an automorphism that does not fix alpha. So, and tau does not fix alpha because data is different. That implies alpha cannot be in the fixed field. See, this is actually the elements from K that are fixed by every element of the Galois group. Tau is a member of this Galois group which does not fix alpha, meaning it cannot fix, alpha cannot be a member of the fixed field, and that is what we are looking for. So alpha does not belong to E implies alpha does not belong to K of the fixed field, and that implies E is equal to K of G of, or that is equal to K of lambda of . Now just want to show that the second result shows that lambda is a 1-1 map. So how do you prove a map is 1-1? We'll take the image. So let E1 and E2 be two extensions of F, and we assume that lambda of E1 is equal to lambda of E2. If lambda of E1 is equal to lambda of E2 implies E1 is equal to E2, then lambda is 1-1. So let us start with E1, and that is equal to K of the fixed field of lambda of E1, and that is equal to K of fixed field of E2 because lambda of E1 is equal to lambda of E2, and that is equal to E2. That implies lambda is 1-1. Our next property that we are going to show is that it is an onto map. This shows that it is 1-1, and this is going to show that lambda is an onto, meaning for every subgroup of the Galois group of K over F, there is an element in the collection of extensions that lambda can map to. This is, by the way, it's E. K is equal to Galois group of K over E. So that means if H is a subgroup of the Galois group of K over F, then H is mapped by somebody. So that extension is K of H is equal to H. The fixed group of H will be mapped to H. So that is a third property. So let us start. H is equal to lambda of KH. And that is equal to lambda of K of G of K over H. Sorry, no. This is what? This is equal to, G of K over KH. So, what we will do is, we'll show that the subgroup which we picked is a subgroup of this. So let us start with an element sigma in K in H. So what does this imply? This implies that alpha of A is equal to A for all A in KH. See, what does this mean? If you take an element from H, or if you take an automorphism from H, and if you try to map A, that should be equal to A, then only that A will be in the fixed field. So, if sigma belongs to H, and if an element have to be in the fixed field, then that sigma should map to itself. And what does this mean? This means that sigma belongs to group of K over KH. What is the meaning of this? All automorphisms on K leaving KH fixed. This actually fixes every element in KH. So sigma belongs to this. So that implies H is a subgroup of G of K over KH. But what we are going to do is, again, this is a subgroup of this. Now the next step we are going to do is, okay, this is a subgroup, but what we are going to prove is H is not a proper subgroup of this. If you can prove that H cannot be a proper subgroup of this, then they are equal. So, that is what we are going to prove. So, K is a finite normal extension of KH. And that implies the degree of K over KH is equal to the index of K over KH, and that is equal to the order of the Galois group of K over KH. And let it be N. And let H contains P automorphisms. say sigma 1 dash dash sigma p, where p is strictly less than n. Because if p is equal to n, then these are same, because this is the order of this group. Now k is a separable extension of kh, because it's a finite normal extension of kh, so it's separable. And that implies there exists a primitive element alpha in k such that k is equal to kh of alpha. See, if it's a separable extension, then you can always find a primitive element such that it is a simple extension. So what we are having here is k is here and kh is here, and alpha is somewhere here. Now we'll create a polynomial f of x equal to pi of I from 1 to p x minus alpha I, sigma I of alpha. See, what are all sigmas? Sigmas are actually sigma i's belongs to h. So they are all automorphisms. So we are automorphisms on k. So you can always map alpha. See, what is the property of this f of x now? F of x is a polynomial such that if sigma belongs to h, sigma is one of these p sigma i's. If sigma is one of them, then sigma of f of x, this sigma is actually, you can write it as sigma x probably. So it's an induced automorphism on k of x is equal to f of x, because the coefficients of f of x are alpha i's of sigma i's of alpha, because the coefficients of x are symmetric values of sigma i's of alpha. See, if you apply sigma of sigma I of something, that will be sigma j of something, because sigma of sigma composed by another after sigma I, it should be another element of one of these sigma i's, because this is a finite group of automorphisms, and it is symmetric in the sense that the powers of sigma i's of alpha are same for all i's. So this implies, so what does this mean? So sigma of f of x is equal to sigma of f of x is equal to f of x. This implies, what does this imply? This implies this f of x belongs to kh of x. Because this is not moved by any automorphism from H. The coefficients of f of x are in kh because it is not moved. That's what it says. So this implies f of x belongs to kh of x. And f of alpha is equal to 0. Why? Because sigma of I of alpha is equal to alpha for some I. Not for all I, but just one I. This is because alpha is a conjugate to itself, and sigma I should map alpha to its conjugate. So in one of the linear factors here, sigma I, for some sigma I of alpha will be alpha. So one of the linear factors will be 0, and it's a finite product of linear factors. One of them is 0, and that is why this is 0. That means the degree of alpha over kh is less than or equal to p, because this is a polynomial for which alpha is a 0. So the irreducible polynomial cannot be more than this. Cannot be more, the degree of the irreducible polynomial cannot be more than the degree of f of x. Now we are almost there. So what we have is degree of alpha over kh is less than or equal to p, which is less than n with this relation, and that is equal to k over kh, the degree. What is k? K is kh of alpha. So that means this is equal to k h of alpha over kh. So what we are arriving at is degree of alpha over kh is less than, strictly less than, kh of alpha kh. This is not possible. If it's a simple extension, k, or you can say any general E of f, if E is equal to f of alpha, then the degree of f of alpha is equal to the degree of alpha over f. Always. Because the elements of the basis that spans or that generates E are the conjugates of alpha. So we arrived at this conclusion. So this is a contradiction. This is a contradiction. And hence H cannot be a proper subgroup of G of K over Kh. And that implies H is equal to G of K of Kh. The first part of the property 3, when we are proving, the video was little blurred. So I'm going to repeat that, just that portion alone. The portion where we had a blurred session is when H is a subgroup of the Galois group of K over F, then we are trying to prove that H is a subgroup of G of K over Kh. This is where the video was little blurred. So what we do is, let us take an element from here. Sigma belongs to H. That implies sigma of A is equal to A for all A in Kh. See, what is Kh? Kh is the fixed field of H. Meaning, if you take any element from H and if you map an element A to A, then that element is in Kh. And that is what exactly it is doing. This element, this A, will be in Kh only if sigma is mapping that element to itself. And what does this mean? This means that sigma belongs to what is the Galois group of K over Kh? Automorphism on K that leaves Kh fixed. So here this sigma is leaving every element in Kh fixed. So this sigma should be in G of K over Kh. That implies H is a subgroup of G of K over Kh. This is the part we had a blurred video. So the first, the second and third results shows that lambda is a bijective map. It's 1, 1 and on 2. The fourth result is very simple if you use the previous results. It states that the degree of K over E is equal to the order of the image of E under lambda. And the degree of E over F is equal to the number of left corsets of lambda of E in the Galois group of K over F, the number of left coset of lambda E in G of K over F. The proof is very simple. The first part is actually, if you know a couple of results, the proof is very simple. So, K is actually a finite normal extension of E. And that implies the degree of K over E is equal to the index of K over E, and that is equal to the order of the Galois group of K over F, and that is equal to lambda of E. So that is all. That is the first statement. The second one, we are going to make use of a previous result. The result is, if K is a finite normal extension of F and E is an extension such that F is a subfield of E, which is a subfield of K, then take two automorphism. Sigma and tau belongs to G of K over F, induces same isomorphism on E if and only if they belong to the same left coset of G of K over E in G of K over F. This means that K, E and F and K, and I am going to write only E here, F here. This says that if K is a finite normal extension of F and E is a field in between, then there are a lot of automorphisms here. Tau 1, tau 2, etc. But when it comes to E, it induces another isomorphism. It doesn't need to be an automorphism because it doesn't need to be. E is not a splitting field of F. E doesn't need to be a splitting field of F. So when it comes to E, it does not need to be an automorphism. It could be an isomorphism. So here tau 1 of E restricted to E and tau 2 restricted to E are isomorphisms within E. They don't need to be equal always. The condition is if they are equal, if and only if they belong to the same left coset of K over E in K over F. See, this is a subgroup. This is a subgroup. K over E is a subgroup of K over F. So what this is saying is T of tau 1 plus K, actually not plus, it is actually composition of G over K over E is equal to T2 after G of K over E. Meaning if you take any representative of this group composed with T1 should be equal to any representative of this group composed with this. If they are equal, then the restrictions are equal. And this portion, this is actually the index. Sorry, this is actually the degree. And degree is equal to index because E is separable over F. So we'll write it here. E is a separable extension of F. It is not necessarily a splitting field, but it is definitely a separable extension because K is a finite extension of E. That implies the degree of E over F is equal to the index. That is the definition of separability. And this is what? This is actually the number of isomorphisms on E. That is our tau 1 of E, tau 2 of E, etc. Every isomorphism is that corresponds to an automorphism here, because you can extend it always. And what is this? This is number of isomorphism is actually these are actually distinct isomorphisms on E. So with this result, this will be the number of left cosets of G over K over E in G of K over F. And that is equal to, we use that notation, G of K over F colon lambda of E. So we are going to prove the next result. The last result we are not going to prove because that is just says that the diagram of the diagram of extensions is an inverted diagram of the subgroups of the Galois group, which we know already. So we are not going to prove that. So this is the last result we will prove. The result is like this. E is a normal or E is a finite normal extension of F if and only if Galois group of K over E is a normal subgroup of G of K over F. And in such case, the Galois group of E over F is isomorphic to the quotient group of K over F over G of K over E. So we'll start with the first one. Before we go there are two things we need to remember here, which you already established earlier. One is a field E is a splitting field splitting field of F if and only if every automorphism on F closure induces an automorphism on. That is one thing. The second result is from group theory. A subgroup H of G is normal if and only if G inverse HG belongs to H for all G in G and H in H. We are going to make use of these two results to prove the first one. So what we need to prove is normal extension implies and implied by normal subgroup. That's what we want to prove. E is a normal extension of F if and only if the Galois group of K over E is normal to the Galois group of K over F. What we know that K is a finite normal extension of E and F and E. And we also know that E is a separable extension of F. It is not necessary that E is a splitting field of F. But if E is a splitting field of F, then E will become the normal extension of E. So E is a finite normal extension of F if and only if E is a splitting field of F. And what does that mean? If and only if every automorphism on K, I am not taking the F closure because K is a finite normal extension of E. So it says separable splitting field. So I don't need to go beyond K. So every auto on K induces an auto on E. With the first result I explained earlier. So now let sigma belongs to G of K over F and tau belongs to G of K over E. This is an automorphism on K leaving F fixed. So this should induce, sigma should induce an automorphism on E. So that means sigma of A belongs to E for all A in E. And what is tau? Tau actually fixes every element in E. So that implies tau of, I'll write it here, tau of an element from E, that is, I'm going to take it as A, that is actually equal to the same element, because tau is from G of K over E. This implies and implied by sigma inverse of tau sigma of A is equal to A. I'm actually composing sigma inverse on both sides. That implies and implied by sigma inverse tau sigma belongs to, this is an automorphism mapping A to A, which means that this automorphism should belong to G of K over E. So what does that mean? For all sigma in G of K of F and all tau in G of K over E, sigma inverse of tau sigma belongs to G of K inverse of K of Galois group of K over E. And that implies G of K over E is a normal subgroup of G of K over F. That is the first part. So we'll prove the second part of the fifth result. So we are assuming now is E is a finite normal extension of F. Then we need to prove that G of E over F is isomorphic to G of K over F, the quotient group G of K over E. To prove this, we are going to use another result from group theory. It's called fundamental isomorphism or homomorphism theorem. The theorem states that if phi is a homomorphism from G to G, G prime, with the kernel H, this is a kernel. Kernel is always a normal subgroup of G. Then G, the quotient group G of H is isomorphic to the image of G. This is the result we are going to use to prove this result. So what we need to do is, see, this is this part and this is our this part. So we need to define a phi, a homomorphism. I will write that result here so that we can always refer. Phi from G to G prime with kernel H, then this is kernel H. Kernel of phi is equal to H, then G of H is isomorphic to phi of G. This is called fundamental homomorphism theorem. So we need to define a map, a homomorphism. group homomorphism. So define a homomorphism by phi from G of K over F to G of E over F. See, you have a K here, a E here, and an F here. You are talking about automorphisms on K. That will become an automorphism here because it's already a finite normal extension. It's a splitting field and separable, so there's no problem. It is going to be an automorphism here. So if tau is an automorphism on K, tau E restricted to E is an automorphism on E. So this is actually an element, this is actually our tau, and this is our tau restricted to E. So that is how we are going to map. So phi of defined by phi of tau is equal to restricted to E. This phi is an onto homomorphism. Onto because for every automorphism here, we can extend that automorphism to onto K. So for the image of that automorphism will be this automorphism. So meaning if you take, let's say, sigma is an automorphism on E, then you can extend this sigma to another sigma prime on K, so that phi of sigma prime is equal to sigma. So it's not to homomorphism. Homomorphism part I am going to leave it to you. Verify it's an homomorphism. Now we have a map, a homomorphism, two groups. This is our G and this is our G prime. So what does it mean? G over the quotient group of G over G prime. Sorry, we need to find out G prime is what? G prime, this is G prime. So we need to find out the kernel. So kernel of phi, what is the definition of kernel of phi? Sigma belongs to this such that phi of sigma is equal to I. The identity of this E over F. What is this? See, this is an automorphism on K, and that should leave all the elements in E. Then only this will become an I on here. If you take an element from E and map with the sigma, that should go to the same element. Then only phi of sigma will become an identity map on E of F. So that is nothing but G of K over E. Because these are automorphisms on K leaving E fixed, and that is exactly what this means. Now we apply this rule. So we have all the conditions here. We defined a homomorphism. We have a kernel here. Then we are using group or using fundamental homomorphism theorem in groups, what we have is G over F, the quotient group of G over F. What is, see, this is G of K over, this is G, right? This is G, K over F. And the quotient H is what? H is the kernel of phi, and that is G of K over E is isomorphic to phi of G, phi of G of K over F. But phi is an onto function. So this is actually equal to G of E over F. The whole automorphism, this phi is mapping the whole collection of automorphism to the whole of automorphism of on E over F, and that is the result. The first part of the property 3, when we are proving, the video was little blurred, so I'm going to repeat that, just that portion alone. The portion where we had a blurred session is when H is a subgroup of the Galois group of K over F, then we are trying to prove that H is a subgroup of G of K over KH. This is where the video was little blurred. So what we do is, let us take an element from here. Sigma belongs to H. That implies sigma of A is equal to A for all A in KH. See, what is KH? KH is the fixed field of H. Meaning, if you take any element from H and if you map an element A to A, then that element is in KH. And that is what exactly it is doing. This element, this A, will be in KH only if sigma is mapping that element to itself. And what does this mean? This means that sigma belongs to what is the Galois group of K over KH? Automorphism on K that leaves KH fixed. So here this sigma is leaving every element in KH fixed. So this sigma should be in G of K over KH. That implies H is a subgroup of G of K over KH. This is the part we had a blurred video session. So I thought